Hi, thanks for watching this presentation of this paper, Learning Neural Proto-face Field for Disentangled 3D Face Modeling in the Wild. Existing 3D face modeling methods can be divided into two classes. One of them is the graphics renderer-based method, where the handcrafted renderer is used to reconstruct the faces. Compared to these approaches, our method recovers more photorealistic results with the help of neural rendering. Another kind of method is based on neural rendering. For example, the nerve-based generative models. These models are sensitive to challenging conditions, while our method is more robust and able to disentangle the identity and expression of a face. Our method is based on the widely used 3D-aware generative model, EG3D. Given an input image, 3D face modeling can be achieved by style code optimization with corresponding poses, and pivot tuning to recover details. Other 3D-aware generative models can be implemented in a similar way. Our motivation is mainly from the phenomenon that this kind of neural rendering methods lack of multi-view prior or reliable assumptions, and thus are sensitive to large pose, extreme appearance, or shadow. Under these challenging conditions, these methods produces distortion or ambiguity of shapes. To address this problem, we use photo collection of the same identity to provide 3D consistent prior for robust 3D face modeling. In summary, our methods can be divided into two stages: neural proto-face field learning and neural proto-face field fitting. In the first stage, we aggregate a 3D consistent face shape from a photo collection using multi-image priors and model its corresponding deformation. This produces a face prototype with disentangled ID and expression. In the second stage, we fit the proto-face field to recover personalized details. In the first stage, our method starts from an in-the-wild photo collection and its corresponding style code for each image. First, we implement an uncertainty encoder to predict uncertainties for each dimension of style code, and thus each image is represented as a Gaussian distribution in the latent space. Then, we perform identity-aware aggregation, which uses the uncertainty to fuse the distributions and obtain an aggregated protocode for this collection. In this way, the consistent shape cues of this identity, which have lower uncertainty, are maintained after the aggregation. Second, we implement deformation networks to model the expression. We use a pre-trained 3D face reconstruction network to predict 3D expression codes, and a global face encoder to get hybrid representations for personalized expression. Then, we feed them to the deformation networks to predict the deformation code, which modify the protocode to represent corresponding expression. Finally, with the modified code and camera poses, we use EG3D pipeline to model a face prototype that has the common face shape but different expressions. The networks are trained under consistency losses, and the EG3D pipeline is frozen. In the second stage, we fit the neural proto-face fields by optimizing EG3D generator. First, we warm up the generator by recovering all the images of the collection, using the reconstruction loss and the geometry consistency loss. This step helps the generator to get rid of overfitting in the early stage of optimization. Then, we feed the generator to one target image under reconstruction loss and appearance consistency loss, which makes the generator recover personalized details of the target portrait. We perform ablation study on the deformation modeling. We observe that without the deformation modeling, the model cannot reconstruct the suitable expression and the corresponding details. The global face representation also helps to recover more precise expression. Then, we analyze the photo collection and warm-up strategy. With more photos in the collection, our method reconstructs better 3D face. The warm-up strategy elevates the distortion caused by single image overfitting. Finally, for uncertainty modeling, we find that it significantly improves the identity preservation. The appearance consistency loss also recovers better texture details. For the comparison with state-of-the-art methods, we observe that our method is more robust to the challenging conditions such as large pose, occlusion, extreme shadows, or appearance, and produces more accurate modeling results. Here we can see that our method predicts 3D consistent results under different conditions. Thanks for watching our presentation.